We're going to talk about transient state. So basically what we mean by transient state, some definition, and I'll do some MATLAB codes here. The MATLAB purpose here, I know that we did MATLAB on lecture 3, but in this part, we'll see MATLAB and let's say how it shows the behavior of the system. Like we've seen that system is stable, system is not stable. But what does that mean in the time domain? What do you mean by a stable system in time and unstable system in time? So I'll go over the lecture real quick. So as an introduction, we have a time response. It's basically the behavior of the system with respect to time. So the output of the system when you subject it as an input, which is a function of time. Usually up till now, we've done everything in Laplace domain. Basically are the same. Laplace domain, we do multiplications and stuff. In time domain should be convolution. And we've seen that doing these mathematical or arithmetic operations in Laplace domain are way easier. However, for us humans, we deal with time. Like Laplace is another domain to make things easy for us, but as humans, we only deal with time. So usually when you have a system like this, and we apply, this is what we call a step input. So that's an input, a unit step function. And this is what will be the output. So in this case, if the output does not go to, let's say, infinity, or as time increases, the output increases, in that case, the system is stable as long as it does not go to infinity. If it reaches high values, then the system is unstable. So time response analysis means subject to the control system. So input that the functions of time and studying their output again as a function of time. So usually the system is, or the response is divided in two parts, a transient state and steady state. So basically the moment when you switch on the system, like here, the moment you apply the input to the system, what will happen? How will the output look like? We said like we have stable and unstable. So in the case of a stable system, it means that the system will start responding to the input to a certain level, and that's what we call a transient state. Transient state that it's within a short period of time, and this is how the system will behave. And steady state, once the time goes to extremely large value, let's say infinity, the steady state will be the output of the system at steady state. So in this case, it is a stable system. Unstable system and steady state, the output will be infinity. So this is how we divide the response of the system into two parts. So that's, as I mentioned, the transient response, and we have the steady state response again after YFT dies out. All right, so usually a behavior of system is something like this. So we have this transient state and we have the steady state. Steady state means that the system will be bounded within a certain region. In this case, it's an example of a stable system. Types of inputs, we've seen that in the lectures. We usually deal with impulse, with step, ramp. A parabolic, we don't deal with parabolic. It will be extremely complicated, but those are the usual inputs. In this lecture today in MATLAB, I'll focus only on the step and the impulse. Okay, so types of system is determined by the number of poles are located at 0 at the origin. So the system type is defined as the order or number of poles of the polynomial at the denominator at s equals 0. So here's an example here. So you just look at the poles here. We have one pole at 0, one at -1, one at -half, and this one some value. So here, since I have only one pole at 0, so that's what we call a type 1. When you have two poles, that's type 2, 3 poles at the origin or at s equals 0, that's type 3. So that's a way of classifying systems. So here is an example here. So this is the time response of first order system. In fact, we'll do an example on this one and we'll see the behavior for this one. Let's see. So in this case, this is the feedback system, something like this. So this is the output. And usually, if you remember in electric circuits, this tau is usually known as the time constant. Again, that's a feedback system, 1 over s tau. We have a unity feedback, and this is the output. We've done the feedback formula, I think, last week. All right, so let's take this example for a step response. So let's assume a value of k equals 5 and t equals 10. So I'll go into MATLAB. So my numerator is 5. And I have at the denominator 10s plus 1. So I have 10 and I have 1. So first, before we do the analysis, is it stable or not? I believe yes, because if you look at the pole, it will be located at negative 0.1. So system should be stable. All right, so let's construct the system. Okay, let me clear everything first to make sure we start from scratch, clear all, close all figures, and CLC to clean the screen. Okay, so I'll run this part. So I have my numerator and denominator, construct the transfer function. Again, you can refer to lecture 3 for this part. How to construct the transfer function. First, you must have a control toolbox installed. Then you apply this function, TF, and to create an object, which is the transfer function. So if you guys remember to check the location of the poles and zeros. So here we have only one pole at negative 0.1, and there are no zeros, so it's an empty value. Now to check stability, the command is stable, so logical 1, that means the system is stable. Now we'll see the impulse response of the system. So first I need to define, again, remember time response, step response, we're talking about time. Now we're talking about the behavior of the system with respect to time. So I need to define a time vector. So here's just an example, it could work out, it could not. So we'll try with a vector of time from 0 to 10 with a spacing of 0.05. All right, and the command is basically you have y as the system behavior, and it will return also the time vector impulse. So it means that find the impulse response. Someone's trying to log in. Oh, yeah. Okay, so yes, so the command is impulse. We can just here check on help. I'm sure you are familiar with MATLAB. And it will tell you here it's the impulse response of a dynamic system, and this is the syntax. All right, so let's apply it. And there you go. I have my y vector and I have my t vector, and basically they should be of the same dimension. So just plot it, and we'll see the system is stable. So notice as the time increases, the behavior it dies out. Let's say, for example, it goes down. It does not go to infinity. So 10, I don't think is the appropriate value. Let's try with 100. And again, let's try it here. And there you go. See that at steady state, the system just dies out. So that's an example of a stable system. So that's an impulse output. That's the output of the system if you apply impulse. What will the output look like when you apply a step function? So step response. Same thing, same transfer function. I just change the input and see how the output. It increases, but to a level that it will come steady at 5. It will stop at 5. In fact, if you look at this function, 5 over 10s plus 1, I will assume that the time domain, the inverse Laplace for that one, is 5 e to the power minus t, and we'll assume some initial condition. So it's going to be 5 by 1 plus e to the power minus 10t. And as t approaches infinity, then in that case, the e to the power negative t will die out, will disappear, and I'll have 5 times 1. So the steady state output is 5. So that's an example again for stable system, and we've seen the output. Let's try with unstable system. So just make this one negative 1. So in this case, I have 5 over 10s minus 1. Again, let's clear everything, create the transfer function. Now, my pole is at the right side of the S-plane. So in this case, my system should not be stable. And let's see the step response. And there you go. As the time increases, the behavior of the system goes to infinity. Try with 1000. it will grow even more. There you go. So in this case, this system is unstable, and but it should be the same whether you apply a step or an impulse. The output will be unstable, or the system itself is unstable regardless of the input. All right, so here it's just a first order system. I have only a linear function, constant over linear function. So let's try to have a system like this, 5, 3, and I will have s squared minus or plus 5s plus 6. So I have two poles at -3 and -2. Okay, so construct the transfer function. Now my poles, I have two poles at -3 and -2, and I have a 0 at -6. System should be stable. And let's see the output when I apply an impulse input. All right, see here, because the time vector is extremely high, 1000, it did not look clear. So I'll try with something like 10. All right, see how the behavior, so this is the transient part. Like remember, we have this time response is divided into two parts, a transient state and steady state. So this part where there is a transition, this is the transient state or the transient response, and this part is the steady state response. Like as the time increases, the system is bounded between certain values. So that's the output of an impulse input. What about if we apply a step input? And there you go. So it goes up, it reaches a certain value here. So the peak is 0.9, then it goes down and it stops right there. So that's again an example of a stable system, and that's the step response. Let's try something like this, 9, and I have a 0 here. So we have s squared plus 9. I'm not sure how will the system, I think this is the case of marginal stable. I have two poles like at -J3 and positive J3. So in this case, see the output, it oscillates. So it does not die out when time is infinity. So we cannot call it stable. And at the same time, it does not go to infinity when the time goes to infinity. So it's neither stable nor unstable. So this is the case what we call marginal stable. And to check my poles, I have 0 at, so I have 0 plus 3i and 0 minus 3i, or j, that's the I is the complex value. So this is the case. I have two poles. I have them right at the y plane or the y axis at -J3 and positive J3. So that's an example of a marginal stable system. Remember, I think yesterday or 2 or 3 days ago, we talked about stability, what we mean by stable, unstable, marginal stable. So this is the case when you have a marginal stable system. All right, so let's continue with the lecture here. So you've done the feedback. So we've seen different responses here. Okay, yeah, so that's an example. There you go. So that's the output when we have like the same example before, 1 over plus, I applied 5 and 10, so I can apply 5 and assume any value for tau. And that's what we have here, 1 minus e to the power minus t over tau. If there's a 5 here, then there will be a 5 multiplied by the whole thing. All right, now that's the impulse response. I think the first one is the step response, impulse response, 1 over t to the power minus t. So you notice that there is an exponential part which explains that the exponentials we got for a simple first order system. Again, that's an example of a ramp input. All right, so let's give more examples in MATLAB for the sake of illustration. So let's assume I have a very high order system. I have 5 here and 9. And let's see if I have 2 here. Will that affect the analysis? Like both the numerator and denominator, they have the same order. They're both polynomials. All right, so my poles, they are on the negative side. Again, we look at the real part. So these one are complex conjugates. So the real part is negative. So I will have 2 poles, then my system is stable. We double check here, is stable, logical 1. So let's try to plot the response. Evaluate. All right, so there you go here. So that's for the step. Let's try the impulse. And let's see how the output will look like. There you go. So again, that confirms our stability. If you were asked where is the steady state region, this one is from, I think, 2.5 to infinity. The transient state from 0 to 2.5. All right, so again, let's try another one. Let's remove the 2. Let's run it and see how the behavior. Okay, let's save it. Again, another example like this, stable, step. Again, so it overshoots. So this is what we call an overshoot, actually. Like the system will behave, then it goes back to the steady state. And let's see if we increase the order here, 5 for the poles. Okay, so stable. All right, looks nice. Impulse. All right, so yeah. So this is actually just a simple, as I mentioned before, this is a simple lecture on like transient state, steady state, and I thought it's better to have it illustrated with MATLAB since we covered MATLAB 2 days ago. Again, it's the same functions we did. A transfer function, PZ map is stable. The only part that I added is when we apply the time domain analysis, and the commands are really simple, just step, impulse, and step to determine the step response and impulse response. All right, so that's it for this lecture. As I mentioned, it's going to be a quick one. So I'll stop the recording. Stop.